is it even possible to get behind a black hole?
There's distortions in the space-time continuum in the vicinity of the black hole, so that the accretion disk behind the black hole has sight lines that come around the black hole to you.
Because it's bending the light around because the gravity is that deep and heavy.
Bending the light around.
That's amazing.
So you're seeing this sort of unfolded image of a black hole in all places.
You can't sneak up on a black hole.
This is StarTalk. Neil deGrasse Tyson, your personal astrophysicist. It's a Cosmic Queries grab bag. And you know what that means? Chuck Nice is right here.
That's right.
All right, Chuck.
The fan favorite.
It's a fan favorite.
It is a fan favorite. The people love the grab bag.
Why?
You know?
We have all these amazing guests and Nobel laureates.
Yeah.
And they keep coming back for the grab bag.
We like to grab them by the query.
And Chuck, we still got Just Smart Enough sitting on our YouTube channel.
That is correct, sir.
That is a all science comedy bit.
Yeah, and it's and guess what? Thank you guys. Everybody's watching it, getting a lot of great feedback. It's my comedy special. It's on the StarTalk main YouTube channel.
We love it.
Please check it out.
It's pushing through 500,000 views, so
yes,
we're feeling good about it.
Feeling good.
All right.
So this is Sumit Sharma. And Sumit says, while riding my bike, I noticed the dynamo that generates light every time I pedal. I think it converts rotational energy into electricity. In space, things stay in motion. What if we rotate a turbine that keeps rotating forever, generating loads of electricity that we can send back to Earth? Or have big solar fields? Why don't we generate electricity in this way?
So two separate things.
Two separate things.
Three separate things. Let's start with the bicycle.
Okay.
I think what she's probably referring to is one of these devices that leans up against the wheel. So let's go back to the middle 19th century.
Okay.
Michael Faraday.
Yes.
He might be the most important person many people have never heard of. Because he invented a way to make electricity.
That's right.
All right. He saw a wire and he connected a wire to a little meter. The meter's not doing anything. Took the wire, passed it through a magnetic field.
Yeah.
Didn't just have it sit there. He moved it. And the wire went like that.
Yeah, the meter went. Boop, boop, boop.
He created current in the wire by passing it through a magnetic field. Okay. So, and that was an odd little toy that he made, and he showed it around. And so this is charming. What a
great little trick, Michael.
Yeah, it's just a trick. And there's a rumored comment where, someone, was it the Parliament, whoever, this is in England, of what value is this to the British Empire?
Indeed, sir. You are wasting our time, I see. And you expect us to use valuable pences and pounds.
And shillings. Don't leave out the shillings. And so the reply, rumored, was, I don't know of what value this will be to the British Empire, but I know that one day you will tax it.
Faraday was gangster. That is amazing.
Yeah.
That is amazing. What a great statement.
And there's another statement in the same vein, and I don't know if he really said this, but it's attributed. Another one said, well, what good is this? And then he says, of what value to the world is a newborn baby?
Oh. Well, you lose that argument because the value is nothing.
No, it's what value will it one day
be.
Well, that's the whole point.
Right.
That's the exact analog.
And that answer could still be nothing.
And that is how all electricity is still made today.
That's right.
All electricity through motion.
Through motion.
Okay.
Yeah.
So
it turns a turbine.
Turbine is wires passing through a magnetic field.
And it creates electricity.
Creates electricity every time.
And I don't care where you are in the world, that's how you get the electricity.
Okay.
That's why windmills.
There's wind turbines.
Right.
There's
steam turbines.
It's the steam that just creates something to spin.
That's all it does.
To go through it. That's what it is. And dams, where they let the water go through.
Yep.
It's turning a turbine.
Even geothermal, they use the heat from the earth itself to heat water to make steam to turn the turbine. It's turbines all the way down, baby.
Well, it's not turbines just to warm your home.
No.
Because you can do something with the geothermal.
Well, you could warm your home with geothermal, nothing else.
Right,
correct.
But you're not generating electricity.
You're not generating electricity to do so.
Right.
Yeah.
Okay, so now, different from that, you have solar panels.
Right.
Where the energy is already there.
That's called the sun, baby.
Okay.
Yeah.
You got it.
It's a solar collector.
You have your photovoltaic cells.
Correct.
And that converts the sunlight directly into electricity. And so, yeah, we can do that in space. China has a plan
to put a big ring and do exactly what Sumit is asking to do.
I don't know if it's a ring, but they're going to put up a solar farm in space.
Well, that's the second thing they're doing. So they have a ring that they're going to do.
I didn't know about the ring.
The ring is the latest thing that they're talking.
You going to put a ring on it?
They want to put a ring on it. That's why they put a ring on it.
All right. So when you're in space, if you're far enough out, then there is no nighttime.
Right.
Because you're not making electricity with sunlight at night.
That's right.
And nor are you making electricity in daytime under clouds.
Correct.
There are no clouds and there's no nighttime if you're far enough out in space. You can always point something to the sun.
24 hours a day.
They would then convert it to microwaves, beam them back down to Earth, to a place that will receive it, and it's free electricity.
And here we are talking about drill, baby, drill.
Still digging oil out of the ground.
Still digging oil out of the ground, and they are talking about putting solar arrays in space.
And we like criticizing them, because they far and away are the largest coal burning country.
Okay.
So it's easy to criticize that, putting a blind eye to what they're actually doing to get ready for the future.
They have coal in China, but they still need more. Okay. They don't have oil, so they need to import that. Guess what you can import? And you're going to own it outright.
The sun?
The sun. Okay. And people are like, oh, solar power it's not really viable. It's not, and I'm like, it's 93 million miles away. And if you lay your ass on the beach, it will burn you. And you will tell me that it's not. Anyway, I'm sorry.
There's the evidence.
There's the evidence that the sun. Okay.
So there you have it.
There you go. Sumit.
All right. Thank you for that.
Way to go, Sumit. Way to get us thinking. All right. This is Siroons.
Don't make me come over there and read that for you. Don't make me grab this.
I think it's Siroons.
Okay, go.
He says, in Sunshine, you said that if the sun were about to run out of fuel and collapse, any amount of atomic bombs wouldn't matter. But what if we could put giant rockets on Jupiter and throw it into the sun? Would that buy more life for the sun? This guy is diabolical. he's like Dr. Evil.
No, he's Lex Luthor.
Exactly. I'm putting rockets on Jupiter.
I don't know what he's remembering that I said. Yeah. Maybe I said it wrong, or he's not remembering it right.
So what he's trying to talk
the
about.
Nuclear bomb. Here's what I'm saying. When the sun runs out of hydrogen in its core,
right,
then the furnace turns off.
Right.
To run out of it means at the place in the sun where it's hot enough to fuse hydrogen, they've run out of hydrogen.
That's it.
Okay?
Right.
All right. Hydrogen is everywhere else in the sun. It's just not hot enough to fuse it.
Exactly.
If you could find a way to stir the contents of the sun, bring outer layers down into the middle,
right,
conveyor belt style, you could feed this nuclear engine with an essentially unlimited amount of hydrogen.
Right.
The amount of hydrogen participating in the sun's generation of energy, I forgot the 1%. I mean, it's tiny. Right. Compared to, the sun is made of hydrogen.
Yes.
90% of the sun, it's 8% helium, 2% other.
Okay, good. Because I'm like, what?
2% other.
I thought it was just, hydrogen and helium.
Yeah, it's mostly hydrogen and helium. So that would be the way to prolong the life of the sun. In fact, there's star clusters in space, obviously, where they're all born at the same time. And so you expect them to evolve synchronously in a way that the high mass stars die first, the lower mass stars die second. There are some clusters where there's a star that should have died long ago and didn't.
Ooh.
It's called a blue straggler.
A blue straggler.
Blue straggler.
I remember when this first started. I'll never forget the time when the little nursery was over here and these other stars came
It's hanging out longer than it should have in that diagram of the cluster.
Right.
Okay? It was in my time in graduate school where people figured out what that was. You know what it was?
What?
A blue straggler is two stars that collided, stirring up their material, giving each other
new energy.
New energy. That's right.
So what I did was I found myself another star. I'm kind of like the Keith Richards of stars. Got a younger star over here and I took his energy. Boy,
How old is Keith Richards? That boy must be 250.
Yeah. Oh, that's super cool.
So
super
we
cool.
know the stirring up would work,
right?
Because these stars live longer than they're supposed to. They're supposed to. But if you throw Jupiter in, that'll help a little. Okay, yeah. But Jupiter, as big as it is still small compared to the sun. By mass.
By mass, right.
So maybe we should just find another star system.
That's it.
We're talking about 5 billion years in the future. If you can't figure a way to get another star, go home.
If we made it that far, by the way, if we do make it that far, let's just call it quits.
We're done here.
If we're here as a species 5 billion years from now, we need to be gone. Okay? Anyway.
Give the rats a chance.
Yes. T-Mobile 5G home internet has some big news you should know about. They now have the fastest 5G home internet according to the experts at Ookla speed test. Now, in practical terms, it means photo backups happen faster, streaming a documentary doesn't stall halfway through, the physics of waiting reduced. What's also notable is that this jump in speed doesn't come with added complexity. Setup is simple. You plug it in and you're online in less than 15 minutes. And the value side of the equation holds up too, with a plan price that's backed by a 5-year price guarantee. So, if you want the fastest 5G home internet with a simple setup and savings that stick, get T-Mobile 5G home internet. Just visit t-mobile.com/home internet to check availability today. Price guarantee exclusions like taxes and fees apply. Fastest based on Ookla speed test intelligence data, second half 2025. All rights reserved. All right, here we go. This is David Everett who says, artificial gravity in movies/TV confuses me. When a starship gets hit by a torpedo, the crew tends to fly out of their seats. If artificial gravity is produced by the ship itself, shouldn't that not happen? And if it does happen, shouldn't the crew get splattered on the back wall when the ship goes into warp or hyperspace?
Okay. Two separate questions.
You
get hit with a torpedo.
Right.
So your artificial gravity is creating a force vector mimicking what happens on Earth. Mm-hmm. And that force vector is always down.
Right.
Let me be precise. That force vector is always towards the center of the Earth.
Right.
For everyone experiencing that anywhere on Earth, it is down.
Right.
Okay.
Right.
Pete Holmes has a gig where he said, the comedian.
Yeah, I know
Holmes,
Pete.
He talks about, well, wait a minute. If Earth is in space, then heaven is just away from Earth.
No matter where you go.
No matter where you are. So if you're on one side of the earth, you can say, I'm going to heaven, and point down. Or go to heaven over there. Because for someone on earth, that's up.
That's up.
That's
right.
up.
Yeah.
But anyhow, if I introduce any other force on you,
mm-hmm.
you're going to jolt from that.
Right.
You're going to feel it.
Same way you would on Earth.
You're going to, exactly.
Same way you would.
Yeah, if you're on a bus and then the bus hits a wall or stops, you'll be jolted.
Exactly.
So in space, with your gravity vector doing its thing, if you get jolted, you'll get jolted. Okay.
Right.
No, we did an explainer on all the levels of acceleration.
Correct.
Yeah.
And I think we ended with splat.
Yeah, it was the jerk.
The jerk.
And we ended with snap, crackle, and pop.
Snap, crackle, and pop. That's what it is.
Dig that up. I'm not going to go over that again. It's all the levels of acceleration that can happen to you.
Yeah, exactly.
So now you want to go to hyperspace.
Mm-hmm.
You need some sci-fi hocus pocus.
Right.
To not be splattered on the back wall.
But not warp. You don't need high sci-fi hocus pocus for warp because that is warping space.
My bad. You are absolutely right. Okay. If you're going to warp space,
right?
That's space doing the work for you.
Doing the work for you.
And you just step across.
Right.
You surf it. So that's not a problem.
Right.
So when they show it, the way to show it cool is the thing is there and then it's off at a thing.
Right.
All right. That'll kill you.
Right. Exactly. Everybody on that ship is dead.
That'll kill your ass.
That's right.
All right? Otherwise, you got to find some other way to sort of navigate the space-time continuum in ways that shorten your distance from where you are to the destination.
Right.
So genuine warp drives, if invoked properly, according to manufacturer specs, you should not be a pile of goo.
You shouldn't be a pile of goo.
Yeah,
right.
At the end of the thing.
Very good.
There's a quick, if I can get morbid for a minute.
Go ahead.
There's a scene in the TV series Expanse.
Oh, I love that.
Where there's a sort of cowboy guy.
Yes.
He's okay. He's being a cowboy, showing off his girlfriend.
Oh my God!
Showing off these maneuvers.
Live streaming.
He's live streaming as he's in this craft, and he's maneuvering, and he's badass. Of course, he's strapped in. When you're in one of these things, you're in a 5-point harness, one between your legs, one on each side of your hip, and one across each shoulder. You know what's not harnessed?
Your head.
Okay. Okay. That's how Dale Earnhardt died.
Yeah.
Okay. He hit an embankment. His head is not restrained. The head keeps going
Snaps,
at 160 miles an hour.
Right.
And the body stays there because it's strapped in.
Yeah.
Okay.
They're all chained in now.
Yeah, they are. Yeah, they have a connection to the
connection to the tether.
He had that option at the time.
Oh, damn.
But
He's
you're
probably too old school for that.
Old school. You're not going to do it. So in the scene in The Expanse, he goes through a membrane.
Right.
Where his spacecraft stops. He's stopped at the membrane, but he doesn't.
Yeah.
And it's pretty graphic. It's a pretty graphic.
But it's kind of cool. Yeah. It's good physics. You learn physics.
That's accurate ass physics.
Accurate physics.
And they would later say, here's why the craft didn't crumble, because he was going really fast.
Yeah.
And then stopped on an instant.
Yeah.
On a dime.
Yeah.
All right.
Wow, it's pretty cool. All right. Very cool. This is Dave Hartman. He says, hey, where's the gravity particle? Everything else has a particle of some sort. What's the deal with gravity?
We're looking for it. Okay. Give us a chance here.
Right.
But the energy of the graviton is really low, and we don't know how to go that low.
Right.
Okay.
Yeah.
That's the problem.
Because gravity is like a super weak force.
It is the weakest force in the universe.
Right.
You know, when you want evidence of that?
Yeah.
Bend down and pick up a rock. Okay. The entire Earth was insufficient to prevent you from picking up the rock.
Right.
Think about that.
Because, the gravity didn't change.
Okay.
That rock is on the ground because of gravity.
Do you know what is 42 magnitudes, powers of 10 stronger than gravity? Electromagnetism.
Oh, my God.
42 powers of 10.
That's incredible.
Which is why you go to one of these magnet doors, you can't open it.
Right. It's true.
It's just two plates of,
Or when you get electrocuted, they can't pry you from the wire.
What? Why'd you get dark? So
I'm sorry. I don't know what my problem is.
No, but the doors that are magnetic, the doors that are magnetically locked.
Yeah.
And when you push a button,
and they unlock.
It's an electromagnet,
right?
And they just unlock.
Yeah, and you cannot open those doors.
Okay.
Yeah.
Maybe if you tried really hard, you risk breaking the door. And that's just the circuitry in the thing itself. And you have all of Earth trying to hold on to the rock. And you thwart it.
And all you do is come by just like, look at you little girly Earth.
Girly Earth.
I pick up the rock so easily.
Let's become Arnold Schwarzenegger. Girly Earth.
All right. Here we go.
Yeah, we presume there's a graviton particle corresponding to gravitational waves. Just as there are photon is a particle corresponding with waves of light. Yes.
And the electron.
Yes. Okay.
For the electromagnetic.
Right. So all of that combines.
Yeah.
So we're looking for it. Just, chill.
Yeah. Get off our ass. Like I'm one of you. Like I have a stake in this game. We'll find it soon.
Like you got your own accelerator.
Like my own accelerator. I mean, yeah. All right, here we go. Michael de la Morena.
That's good.
Shouldn't it be Miguel? Michael?
Miguel. Don't tell the man what his name should be.
All right. Is time a dimension or a field? It seems more like a field because it can be affected by gravity.
You know, I like that.
Yeah.
I like the way
he's thinking of time.
Miguel is there. I like that. I don't know that I have a good answer for that. The idea that gravity can distort time.
Correct.
In the way, the way things interact in fundamental physics. There are fields that affect particles that affect fields. So that's an intriguing thought. And I might bring that up with
Brian Greene.
Yeah. We scheduled a session for him where we're going to pick his brain for 3 hours.
Yeah, it's going to be a long session. I'm going to smoke weed that day. All right. It's a good.
We're going to poke his brain. I don't know how much brain will be left by the time, but we're going to get all in it.
Yeah.
It's an interesting concept.
It's a really good concept.
Yeah. But for now, we think of it as a dimension in which we are trapped in the present. And you know the rest of my quote there.
Go ahead.
We are prisoners of the present.
Yes.
Forever transitioning between our inaccessible past and our unknowable future.
It's a really great quote. It's really good.
I'm just saying.
No, it's great.
We're kind of stuck.
Yeah.
But you're not stuck in space.
Right.
You can move this way or this way.
Space any way you want.
Jump up and down.
Right. Any way you want.
So one day, if we can conquer time, we'll have access to our entire timeline.
Right. I only want to see parts of my timeline. I'm going to tell you the truth. All right, this is Textile Wiz. He says, hypothetical, Neil. You're given 40 yards of 0.15 millimeter steel wire on a reel with no markings. Would you use it as fishing line or listen to the 1 minute message it may contain? How could you possibly know it contained information?
Why would there be information in the wire? Why is that even a thought? Okay, by the way, if every part of the wire is identical to every other part, it cannot contain information.
Why not?
Because information is this configuration of whatever you have is different from this configuration, is different from that configuration. Right. And the information is contained in the difference in these configurations. That's where you get information.
That's where you get information.
If it's identical,
right, there can be no information because it's all the same all the way through.
It's all the same all the way through. Or the only information it's giving you is what's the orientation of the atoms that give you the string.
Correct. Yeah.
Okay.
Right.
And often that repeats.
Yes.
Typically,
and it normally is.
Like in a crystal, the patterns repeat.
Right.
So you only have information enough worthy of one of these patterns because once it repeats, it's not more information.
There's not more information. It's right. It's just a repetition.
So Chuck, that's the difference between having 2 newspapers and 2 oranges. Okay.
Right.
2 oranges, you got 2 oranges.
2 oranges.
2 newspapers, you don't have twice as much information.
Right. You just got 2 newspapers.
You just have 2.
But they got the same information.
The same information.
Gotcha.
Okay.
Right.
Yeah. So I don't know how information would be embedded in the wire. And I have to know that in advance to even attempt that.
Right.
But clearly that's what I would do if I had any suspicion.
If you had any suspicion. So the answer is go fishing. Right?
Is that the answer?
No, that's not the answer.
But it's a steel wire.
It's a steel wire.
That's a big fish.
I don't know what you're catching. We catching some tuna, some sailfish.
What's the difference between a sailfish and a sunfish?
Oh, the sunfish are the big giant fish with the funny looking heads.
What's the one with the
thing? And that's the sailfish.
So what's the sunfish?
The sunfish is the big, like fat, like it's just got a big, fat, long head.
Okay.
That's the sunfish.
I'm just a city kid.
And little teeny. All right.
Okay.
All right, here we go. Stephen R. Small says this. Assuming spiral galaxies are evenly distributed, I'd predict an even split of spirals turning counterclockwise versus clockwise, plus a small fraction on edge where spin can't be detected. What would be learned if that prediction were true or not? And putting aside expansion of space, is a galaxy's translational travel vector aligned with its equatorial plane like a frisbee?
For the longest time, people have wanting to use these massive data sets of galaxies in the universe to see if there's an orientation of the spiral galaxies.
Right.
One way or another.
Right.
Because they're going to spin.
Yeah, they could spin.
That way.
Right. And they can spin edge on, flat,
right.
All kinds.
And who is this that asked the question?
This is Stephen R. Small.
So Stephen presumes that if it's edge on, you wouldn't know which way it's spinning, but we do.
Oh.
Yes, you can put a slit across it and get its spectrum, and you'll see that one side of the galaxy is blue shifting towards you, and the other side is red shifting away.
That is brilliant.
Yeah, yes. My people are brilliant.
I love that.
My people are brilliant.
That is so cool. But go ahead.
Yeah. So you know if it's coming towards you, even though it's edge on.
Right, even though it's edge on.
Yeah, okay.
You can see what's blue shifted, what's red shifted.
So another fact I must correct is if you randomly scatter spiral galaxies into any environment, the most likely way you will find them is edge on. So here's the dish that's the galaxy.
Okay.
Here's a face-on galaxy. So let's say the North Pole is pointing to your head. All right. That's also face-on.
Correct.
The North Pole is pointing that way. To get a face-on galaxy, the galaxy has to be facing you to be a face-on galaxy.
Right.
Or it could be the other way.
The other way.
So there are only two ways the pole can be pointing if you get a face-on galaxy.
Exactly.
Okay? Edge on, oh my gosh.
Oh, you can go all the way around the clock.
At edge on, the pole
anywhere you want to go.
Can be an entire circle.
Right.
This way, and you are edge on the entire way. There are more ways to configure edge on galaxies than face on galaxies.
Okay.
In a random set of galaxies.
Absolutely.
Okay.
Yeah,
and you can show that probabilistically and statistically.
Cool.
And it's an exercise in graduate school. You do this. So don't be surprised when you look at the Hubble Deep Field and other things. There's a whole lot of edge on galaxies.
Right.
Okay.
Right.
People have been looking for extra rotating one way versus another. And the first time someone made that claim, they had room full of people checking which way is the galaxy rotating. Just they ignored the edge-ons. So which way is the galaxy rotating? And people made their catalog. They said, oh my gosh, there's a net rotation clockwise. Holy cow, what's going on? And then theorists started coming in. Maybe there's a leftover rotation from the Big Bang. And people started jumping all in. I call them ambulance chasing theorists. Okay.
That's funny.
All right.
Go ahead.
So then someone had the idea, let's give this same test to a different set of people, except have them look at the photos from the other side, the mirror image of the photo.
Mirror image, okay.
They evaluated the thousands and thousands of galaxies. Once again, most of them were rotating clockwise.
Right.
That's not possible. I just flipped them all on you.
Right. That's a mirror image.
Right. So they concluded that there's a psychological preference for noticing.
So we have a bias.
We have a visual bias.
We have a bias that allows us to look for that.
That's right. And so we said, we're not going to have humans doing this ever again.
Right.
So we train computers. AI is coming in at the time.
Course, right.
And someone now has a section of space, not the all of sky, a section of space where there's a net angular momentum a net spin in one direction and not another. And that's in the last year or so.
Okay.
So check that out. And we think it's not going to hold up, but it's nonetheless an observed result that people are contending with. Yeah.
Well, Stephen, way to go, man.
And we're using spiral galaxies because elliptical galaxies don't have the stars are like beehive.
They're doing all kinds of crazy crap.
Right. It's not really
Whereas the spiral galaxies are uniform.
It's a uniform rotating system.
Which by the way, we're in one.
We're in one. We got one.
There you go. That's our home. Little known fact about me, I'm an entrepreneur, but I come from a family of entrepreneurs. My father was an entrepreneur, my grandmother was an entrepreneur, and my great-grandmother was an entrepreneur. I know how hard it is and how scary it can be, and you're not entirely sure it's going to work out. And it can be hard to make that leap of faith. That's why it helps to have a partner like Shopify by your side. Shopify is the commerce platform behind millions of businesses around the world and 10% of all e-commerce in the US. From household names like Death Wish Coffee and Magic Spoon to brands that are just getting started. With hundreds of ready-to-use templates, Shopify helps you build a beautiful online store that matches your brand's style. And get the word out like you have a marketing team behind you. With Shopify, you can easily create email and social media campaigns wherever your customers are scrolling or strolling. It's time to turn those what-ifs into sales with Shopify today. Sign up for your $1 per month trial today at shopify.com/startalk. Go to shopify.com/startalk. One more time, that's shopify.com/startalk. And I want to be a silent partner in your business because you're going to be very successful. All right, this is Jose Ikamba. Jose Ikamba, who says...
By the way, is there an accent over the E?
Yes.
Okay, because I knew a guy who took off the accent. He just wanted everybody to call him Joe's.
Josie.
No, just Joe's.
Joe's.
And that felt wrong.
That's wrong.
That's what he wanted.
Joe's.
Joe's, okay.
Yeah, no, that sounds weird. Jose says, in Fantastic Four, First Steps.
I remember the day that movie premiered. It was highly advertised. It looked intriguing, looked even fun. Haven't seen it yet.
Still haven't. Me either. He says, Reed Richards considers teleporting Earth into another universe to save it. Realistically, with current technology, what could humans do to move Earth from its orbit around the sun, analogous to DART or Dimorphos, but on a planetary scale? How plausible is it?
You got to really understand how much mass there is on Earth.
Tell me about it.
Okay. I did a calculation. Do you know they bench test rockets?
Okay.
Space rockets.
Okay.
In the desert. So you know how they do that? They could point them upwards and see how far they go,
right.
But they don't. They anchor them to Earth, ignite them, and measure all the forces and the pressures and the temperatures and everything. And I thought to myself, if they kept doing that,
we could increase the rotation of the Earth.
I said, are they slowing Earth down? Because if it's perpendicular to our rotation, that would have a different effect. It wouldn't speed us up or slow us down.
Right.
But if it's due east or due west, oh my gosh. So I ran the calculation.
Not going to happen, huh?
It's not going to
happen.
It's nothing.
Right.
Compared to the rotational inertia of the Earth. So
it's a mosquito punching an elephant.
Not even.
Not even
a gnat. It's a gnat.
A blue whale.
Give me something bigger than an elephant.
A gnat in a scuba gear punching a blue whale.
Yeah, so it's not a thing. So, but as I said in other recordings we've made, there's a movie made in China, but with an international cast called Wandering Earth 2.
Okay.
I never saw Wandering Earth 1.
I haven't seen either.
Okay, but Wandering Earth 2, there's something wrong with the sun. They got to take Earth somewhere else. There's no teleporting. It's kind of in present day, actually. Maybe a little bit in the future where they have space elevators and things, but it's not it's not Star Trek future.
No.
All right? They got regular rockets. So they said, we got to move Earth. And they set up these rockets around the perimeter of the Earth, all pointing the same way. And then they ignite them all. And then Earth slowly pulls out of orbit.
Road trip! And where
99 bottles of beer on the wall to another star system to enter ourselves into their orbit.
Wow.
Now then you could choose where to put the orbit.
That's true.
Get the right exact temperature.
Exact temperature, everything you want. And wait, and the closest place we could go, which is not even a real star though, right? Isn't that Proxima?
No. Alpha Centauri is a system. Proxima Centauri is the closest star within the Alpha Centauri system.
That's what I'm saying. So we would have to go to Proxima. We would have to go to Proxima because that's the closest we would.
Yeah, for every star, there is a distance that would be the right Goldilocks distance.
Right.
So we can pick any star in principle and just go to the spot.
Go to that spot.
Yeah.
Okay.
Yep.
All right. So this is Tam Tam. Hey, Tam Tam. In relational physics.
This is very like psychotherapy.
This is, yeah.
What?
In relational physics, tell me about EMC squared. How's it make you feel?
How's it feel?
How's it?
Makes me feel good, actually. Okay.
When different observers describe the same process differently, what is considered invariant? What actually holds across those perspectives?
I like that.
Wow.
You know what's invariant? That's a great point. Because two people seeing the same thing, interpreting it differently. Is there anything that's constant?
Right.
Yes. The speed of light.
Look at that.
So no matter what's going on, if they measure the speed of light, they're going to get the same answer.
Oh, look at that.
Now, there are other invariants. That's the simplest one I could describe. There's others where there's a combination of your light, your travel in time and your travel in space. And so the length of that vector is the same for all the observers, if I'm remembering this correctly. I'm going to check with Brian Greene again on this, but the combination of those two is invariant. So for me, my space vector might be longer than my time vector relative to you. You can have a longer time vector relative to space vector, but to connect the two ends, that length would be the same. And that would be the same throughout the system.
Interesting.
I think I'm getting that right.
I got
It's been
you.
a while since I dug into it.
Right.
But you see what I'm saying? And so just look at a triangle,
Yes.
and the hypotenuse of the triangle would be an invariant. But the triangle that gives you that hypotenuse can have varying to the legs can be a different size relative to each other.
Exactly.
And these two legs, one is time and one is space.
Oh, okay.
Yeah.
All right. Now that's a very good way to explain it.
Yeah.
Does that make sense?
If that works out. Yeah. Mhm.
Okay. Wow. Tam. Like,
That's a good, deep question. And
now, let me tell you what
invariance.
Tam's doing. She's like, can you do my physics homework?
Is that what that is?
That's what
and
that
so
is.
invariants are the things that would be constant, and you want to know what those are because those are mathematical jump points from one observational system into another.
Wow. Look at these people.
I know. We got some good people.
I'm telling you, these people are on.
Okay, we got like 5 minutes left. Give me do you think we could fit 2 in there?
Diana Smith says, how can galaxies collide if everything is moving away?
Oh, I love that.
More precisely, how is it that while the universe is expanding and moving away from us, the Milky Way and Andromeda will collide in the near future?
Okay, you ready for this?
Uh-huh.
You ready?
Go
Okay.
ahead.
So galaxies that are near each other feel each other's gravity.
Right.
And they have speeds in response to that gravity. All right. So I'm going to pick a number. Let's say 200 miles per second.
All right.
Okay. Let's just say, so that's a characteristic that goes much higher in galaxy clusters. Let's just say, picking a number, 200 miles per second. These galaxies feel each other and they're moving around each other. The universe is expanding. Well, the bigger is the distance between two objects, the faster it's expanding. If I'm not far away enough from this system for the expanding universe to be greater than 200 miles per second, the expanding universe will not manifest in this system.
Right.
If I go far enough away so that the universe is expanding 400 miles per second, it's going to rip these galaxies apart.
Exactly.
So galaxies nearby each other are not spread over enough space in the universe for the expansion of the universe to manifest.
Oh, gotcha.
However,
Uh-oh.
in the Big Rip,
Okay.
the accelerating universe,
Yes.
there's a point where the expansion of the universe will rival the relative speeds of galaxies that are near one another, and it'll rip them apart. And then it'll rival the speeds within the scale of the galaxies themselves. It'll rip the stars apart. Then it'll rip the planets off the stars. Then it'll rip the atoms out of the star. Then it'll break the atoms apart. Then it'll break the electrons off the atoms. Then it'll break the nucleus apart.
And that is because the acceleration is constantly increasing.
Constantly increasing.
Right.
And it'll outstrip anything.
outstrips anything.
Anything that would otherwise be holding
You
itself
can't
together.
outrun it.
Can't outrun it.
Can't outrun
That's
it.
a good way to say it.
Yeah.
So that's why only nearby galaxies will ever show a blue shift.
Oh, look at that.
Yeah.
That's very cool.
Yeah.
Good stuff.
And it's only when the red shift outmuscles it.
Right.
And so no faraway galaxy has a blue shift.
Has a blue shift.
Nope.
Look at that.
Yep.
Wow. Diana Smith. These people are very smart.
And we are on a collision course with Andromeda.
Andromeda, right? Because we're close enough.
Yeah, in like 7 billion years,
Yeah,
plus
there
or
you go.
minus.
Yeah, so stick around, Diana.
October 3rd. It's 7 billion years.
All right. Bill says, in the classic depiction of a supermassive black hole, e.g. interstellar, the accretion disk looks aligned flat, horizontally from our point of view. Does a black hole look the same from all sides, left, right, top, bottom? Doesn't make a difference. And is it even possible to get behind a black hole?
Yeah, so I'm impressed that he called that a classic description.
Right.
That's only been with us for like 10 years or so.
Right.
Ever since we've had enough modeling, enough physics, enough theoretical understandings. So I'm impressed that that's now classic.
That's classic now. That's funny.
And it looked like you were coming in on the accretion disk,
Mm-hmm.
but there's distortions in the space-time continuum in the vicinity of the black hole. So that the accretion disk behind the black hole has sight lines that come around the black hole to you.
Because it's bending the light around because the gravity is that deep and heavy.
Bending the light around.
That's amazing.
So you're seeing this sort of unfolded image of a black hole in all places.
You see behind it when you're in front of it. You can't sneak up on a black hole.
So you can go behind the black hole,
right?
But then I'm going to see your ass in front of the black hole,
right?
Because the light travels there. And when you see curved light, you don't know that it's curved,
right?
As far as you're concerned, it's a straight line.
Damn.
Just like when you see the sunrise,
right?
The sun isn't there.
Yeah,
the sun is 5 minutes below,
right?
Because the light refracted. It's not for the same reasons, but I'm saying if the light bends and you see it, you don't see bent light.
Right.
You're
seeing the light.
You're seeing a straight line. What you think is a straight line.
Because that's why you see it.
That's where you see it. And it's the refraction of the atmosphere that 5 minutes later the sun actually rises, but the atmosphere bent it into your view and you think it's in a straight line.
Woo!
So that's so cool. That's what's going on
That's
there.
what's going on in the black hole.
You can see all sides of the thing.
That's dope.
Totally dope.
That is amazing. Ooh, I love it.
I answered that quick, didn't I?
Yeah, you did.
Whoa.
Yeah.
I answered that quickly.
Yes, you did. Thank you for doing that. My mom would be very
upset. Your mama was a grammar Nazi.
Yes, she was.
Okay.
Yeah, my house was a hellscape.
That's why you're so well spoken.
Oh yeah. Oh.
You know, one of my favorite shirts is?
What's that?
A librarian. I saw a librarian wearing it. Okay.
Right.
Well, I don't know if she was a librarian, but she looked the part.
Okay.
I was at a book festival.
Right.
Or I'm signing books.
Right.
She's walking around.
Right.
Kind of middle-aged.
She had a card catalog behind her.
Card catalog.
That was on the Dewey Decimal System.
You know, she had the glasses with the thing, right. And the hair was in a bun.
Right.
Okay.
Yeah.
But she wore a t-shirt. And librarians don't wear t-shirts.
No, right.
This t-shirt said, "I'm silently correcting your grammar."
That's cool t-shirt.
That's gangster right there. Right.
Yeah.
So, Chuck, that's it. That's another.
That was a great episode.
Man.
These people are they're bringing it with the questions.
Bring it in. Bring it on. Bring it in.
Yeah.
Another completed episode of Cosmic Queries Grab Bag Edition. Thanks again, Chuck.
Always a pleasure.
For being here. Neil deGrasse Tyson, your personal astrophysicist. Keep looking up.